In this problem, there are two parts. In part A, for the particle in a rectangular well, it's given in section 2.4, we need to verify that B is actually equal to E0 plus E to the power half times A divided by E to the power half. So if we go back to section 2.4 on page 29, we can see that there is a statement that says from psi 1 of 0 equals psi 2 at x equals 0. From this, we find that C is equal to A. Okay, and if we equate the first derivatives of psi 1 and psi 2 at x equals 0, this should ideally give us the value of B. So they don't actually equate, take the derivatives and then equate them at x equals 0 and then show this. They just say that if we do this, if we did this, we end up with this equation for B. Now we are actually going to do that and show that that it indeed brings us to this equation for B. So before we get into that, psi 1 is gonna be C times e to the power 2m over h bar squared to the power half times this value, and psi 2 of x is gonna be a cos so this is psi 2 and this is psi 1, and we know that C is equal to A, right? So I'm just gonna remove C from psi 1 and write it as A. So if we actually want to derive that C is equal to A, we can just do this. The wave function should be the same at the boundary because we don't want any discontinuities in the wave function. So the wave function in region 1 and wave function in region 2, they have a common boundary at x equals 0. And at that point, the wave functions are expected to be equal. So psi 1 of 0 is going to be C, because we initially had C here. We're going to prove that C equals A in a moment. And x is equal to 0, right? So if this is 0, we essentially have e to the power 0, which is 1. So it's just going to be C times 1 is equal to A times cos of 0, which is equal to 1, plus B times sine of 0, which is equal to 0. So this whole term is equal to 0. So this is very clear that C is indeed equal to A. That's very easy to show. Now let's work with the first derivative of psi 1. So that will be A, because C equals A times, because we're taking a derivative with respect to x, it's gonna be e to the power, we're taking the derivative of an exponential, so we're gonna get back the exponential times, now let's take the derivative of what's in the power. That will give us this. So this is the first derivative of psi 1. Now for psi 2, the first derivative is going to be a times. Derivative of cos theta is negative sine theta. So times, we have to take a derivative of what's inside this, and that's going to be plus derivative of sine theta is cos theta. So we get something like this. So these are the two derivatives, and we have to equate them. They're both equal when x is equal to 0, right? So that would give us a times, when x is 0, this term here will become 1 because it's e to the power 0, and that's going to be 1 times this value remains the way as it is. Now, when we plug in 0 here, right, this will give us sine of 0, which is 0, right? So it's going to be negative a times 0 times whatever you have. It doesn't matter. It's all going to be 0 plus b times. If you plug in x equals 0 here, you're going to have cos of 0, because sine of 0 is 1, right? So you're going to have that times this. Now this term is completely 0, so we ignore that. And I am going to just erase it off, right? So we end up only with this. Now I can basically cancel out this term and this term. They're essentially the same thing, right? So that would give me a times this. That's, yeah, that is exactly what that would give me. Now, everything, if I have to write b in terms of everything else, that's going to be a times v0 minus e to the power half divided by e to the power half. And this is exactly what we were supposed to verify, and we verified that. So this is the solution to part A. Now, moving on to part B. We are asked to verify once again. This time it's equation 2.33. So this equation 2.33 is on page 29. Here, if we just read the statement right above the equation, it says that taking the first derivative of psi 2 at L and equating it to the first derivative of psi 3 at L, and later dividing the whole thing by the value of psi 2 at L equals the value of psi 3 at L. Now this and the value of b that we just found here, the fact that b is equal to this. So this combined by with expressing b in terms of a is gonna get us to equation 2.33. And that is the equation for energy levels. These two would combine to give us the equation for energy levels. Cool. So let's start. Let's just write down psi 2 of x. Psi 2 of x is a cos 2m over h bar squared to the power half e to the power half is x plus b sine this. Now psi 3 of x, that is a simpler term, e to the power negative 2m over h bar squared to the power half times v0 minus e to the power half times x. So psi 2 of L is equal to psi 3 of L. And why is that the case? Because the wave function needs to be continuous, and psi 2 and psi 3 have a common boundary but, at x equals L. And at that point, we expect them, the wave functions to be the same and the derivatives to also be the same because the wave function has to be continuous. So, okay. So this would give us, when we substitute x to be equal to L, we have a cos times L plus b sine of 2m over h bar squared. I'm actually going to put these two together because they're both raised to the power half. This should be equal to g times e to the power negative 2m over h bar squared times L. So these terms should be equal, right? Now, if we were to take the derivative of, we have actually taken the first derivative of psi 2 of x, which is here. I'm still going to do it anyway. That's going to be and the first derivative of psi 3 of x is going to be this. So this would be the derivative, the first derivative of psi 3 of x. Now we have to equate these derivatives when x equals L. So that will give us minus a times, let me actually do this. So I am gonna call 2me over h bar square to the power half to be equal to, I don't know, it's really hard. Maybe I'm just gonna call it d. Or maybe small d, just to, I'm gonna call it d. So I don't have to write it in full every single time I do something. It's gonna be sine of dx times d So this is going to be dl plus b cos So this is what it's going to be. Now we have this right here, and then we have another equation right here. So the goal is to divide this equation by this, okay? And that would potentially give us, let me actually write this down. I guess I'm gonna write, yeah, let's just do this. D times O is D is B. Now I am gonna divide the left-hand side with the left-hand side of this equation, which is, it's gonna be A cos D times L. Let's be sine D times L. And that will be equal to G times e to the power negative 2m v0 minus e times L over h bar. Yeah, it's exactly that. So here, first things first, let's cancel out some things, right? We can cancel out this term, the huge exponential term, which is such a pain, and the g, right? And once we do that, now we're gonna write b in terms of a. This is b. So I'm gonna plug that into this equation. So I have So I'm going to write this as v0 over e minus 1 to the power half. Right? So I can write it as, and e over e is basically 1. So it should be equal to negative root 2m v0 minus e over h bar. I'm going to divide this by this part. It's going to be a cos d times L plus a sine d times L times v0 over e minus 1 to the power half. Now let's cancel out a. Okay, so once we cancel out a, we can maybe group the terms together and see what happens. Now, let me just remind that d is equal to this value, just so that we don't forget it. Now, what I'm gonna do is, I'm actually gonna write this term right there to be under root 2m times this. I'm just splitting out things in the root. And the d here and the d here can be written as root 2m over h bar times root e, root 2m over h bar times root e, right? And now we can cancel out root 2m here. We can cancel out the h bar, right? So this would give us this will be equal to negative. I'm going to multiply this with that. So I'll get something like this. Once I have this, I'm going to get the sine terms on one side and the cosine terms on the other side. Okay, that would give us, if I brought the sine term to the left-hand side, it's going to be so here I can basically cancel out those two e to the power half terms, and this would give me sine times v0 minus e so I'm gonna multiply this and divide this by e to the power half. So I get this. Now this will be equal to actually hang on. So if we look at it, it's just yeah. So it's just 2 times v0 minus e to the power half times cos of d times L. So what we have is very close to what we see in the equation. Now let's just work with the right hand side. Okay, if we only worked with okay, before we get to that, I'm actually gonna multiply both the sides of the equation with an e to the power half. So yeah, we end up with this. Now I'm gonna work only on with the right hand side of the equation, right? That will give me sine of dl times v0 minus e minus e. So this will be sine of dl times v0 minus 2e, right? And the left-hand side is I don't think we can simplify that anymore. So I'm gonna write this be equal to -2 times this. Now I can multiply both the sides of the equation with a -1. Negative and a negative give you a positive, and I can multiply the -1 with this term to give us 2e minus v naught times sine of, the value of d is 2me under root over h bar times L is equal to 2 times, because these two are both raised to the power half, I can multiply them together, right? So it's going to be v0e minus e squared to the power half times cosine of root 2me over h bar times L. And this is exactly equation 2.33. So by doing some cool math, we ended up with equation 2.33.